Okay, this is just a quick demonstration on how to use CCM Plus for electroplating. So the parameters are kind of random, just to quickly get a model set up for you. So here in SolidWorks, I've created a kind of a nozzle type geometry, and I've also put in an anode there, and there's the nozzle geometry, solid models, so I can save them. And then I go to CCM, and we start a model. So we go to the geometry and we create a new geometry. Then we can import the geometry we just created from SolidWorks, or you can create a geometry inside of this actual package. So I'm going to create this, import this model 2. Okay, so that's the geometry that we just got, the cathode and the anode. So we need to do a couple of operations. We brought them in as two bodies there. So what we can do, we just subtract one body from the other, and the tool, we want the tool to be the anode, and the target body is the cathode area. So we'll keep the tool and we imprint. These are things that you'll learn about. So now we have a new model here, subtract bodies. So we've done that operation. We can go to that part. Let's create a scene here so we can see the geometry. So we go to this that we just created, which is the cathode geometry with a hole in, because that's where the anode would go. So we just want to create a new geometry part from that. So what that does is, this is your CAD area, and then you kind of take the interesting bit out to what's called the parts, and now we have something that we can work with. So we have all these surfaces in parts, and what we can do, we can split them up and identify them. It's called split by patch. So I can name that anode, create, and then I can just name that one, control and select that face, and I call them, we'll call them ends. So that's took them out, and now we're just left with the nozzle walls. So we just name them nozzle walls. Okay, so now we've created that geometry. So what we want to do with this body, we then say, okay, assign parts to a region. A region is something that you're going to create a model from. So we've done that, and now we can do an operation. We say do a mesh. So we do, where is it, new mesh, automated mesh. So we choose that body, and we have mesh parameters here. It's going to be a quick rough mesh. So inside the mesh parameters, there's some default controls. Let's say a cell size of 5mm. Oops, come here. 5mm. And what we can do is we now mesh that. If the workstation you have is multi-core, you can go to the mesh, and instead of serial down here, we can choose parallel, and it'll take advantage of the multiple cores. So there's your volume mesh. Okay, so now you have your volume mesh. So now we need to create the physics. So what we do, we have what's called continua. Select the models. It's just going to be steady state, liquid, segregated flow, constant density. We'll call it laminar. We're not really interested in flow at the moment. We're actually modeling the electrochemistry, the plating on the walls, electrochemistry. Actually, we'll just do primary current density distribution. So we just choose the electrodynamic potential for the moment, just for this quick demo. So we've created those models. We have to go into the description of the liquid. It's going to be an electrolyte, so I'll rename that electrolyte, and we're interested in this electrical conductivity. Let's say it's 30 Siemens per meter. Okay, so now on the regions, now that we've set the continua, we can choose the anode and the nozzle. By default, they're insulator. You see here, insulator. So we choose them two, and you can set polarization curves. I'll just set a particular constant electric potential, and we'll just set the anode to a value of, the default is 0, we'll just set it to 2. Cathode is by default 0, you'll see here, there. So we set the potential, so we can just save that model. We set the conductivity of the electrolyte, and we're not going to model for flow. We don't have to model for flow. We're just doing the electrodynamic model. So let's see what we got. Solvers, the flow, and I can just freeze that. It's just wasting time doing that. So we can initialize, and then you press this little guy here to start iterating, and it runs very quickly. You can see residuals are down to 10 to the minus 10 and not very long, so it's very quick. There we go, it flattens out. Let's stop it and save it. So we create scenes in order to kind of visualize those results. Let's go section plane, there we go, and we want it normal to Z, and we can just create that. And then what we can do, we can create a scene scalar, and we're going to, in the scene scalar, we choose, there's lots of things you can choose, and I'm going to choose electric potential, and I'm going to display on that plane I just defined, and there you go, you get the potential distribution. You can move this around whichever way you want it. You can split these windows up and work with different windows. So what we can do is we create another scene scalar, and let's look at scalar the current on the wall, you know, the electric current density. Boundary specific electric current is a current density on boundaries. So we do that, and we're going to choose the part on the walls, nozzle walls. And there you go. So what you can do, you can define yourself, this is in amps per meter squared. We can easily change that if we want to amps per decimeter squared, really easy, and you know, display it in different ways, or plating, thickness, there you go, very easy and quick actually. Another neat little tool is that you can do a report. So you go down to reports, new report, and there's all these things that you can do. Here's a cool one, surface uniformity. So we're going to do the surface uniformity of the boundary specific current, and we're going to do that on the cathode, the nozzle walls. And if you right click and run, and here you got this uniformity of 0.69. Ideal uniformity, if it was completely uniform, it would be 100%. Here it's 0.6. That could be a parameter you could, you know, monitor. There's lots of other things you can do as well.